Okay. So we first start with the Newton's law of gravity. Law of gravitation, right? Gravity, gravitation, gravitational force, right? Basically says that, I mean, let's start with this. I mean, that's the basic statement. So let's say 2 point particles with masses M1 and M2. Why do I have to write this thing down? But let's just write this thing down. 2 point particles with masses M1 and M2 and separation R attract each other. With F force. F equals G times M1, M2 divided by R squared. Okay, so that's basically the statement in here. But let's just remember this. It doesn't matter what these particles and positions are. They apply, the magnitude of the force they apply to each other is going to be the same. So there are two forces. These are action and reaction, if you want, in Newton's third law. So both of these forces are equal to each other. They are opposite, obviously, as vectors. In any case, they have the same magnitude. Okay, so that's the statement in here. Okay, so here G is the Newton's law, gravitational constant. Its numerical value is 6.67 times 10 to the minus 11. And the unit is Newton meter squared per kilogram squared. Right, so that's the gravitational constant. Okay, it is also known as the worst fundamental constant. Fundamental constant with the worst known value. So I think this is kind of the best value known. So I may say something about this. So this is actually quite hard to measure, even though this is one of the fundamental constants of nature. It's quite hard to measure. I may say a few things about these. How we obtain G. So somebody measured, Cavendish has measured it. Let me talk about this actually. Okay, so in any case, so there are a few things in here. First of all, these are for point particles, right? We first start with the point particles and as did Newton, basically. Second thing in here is that the masses enter in here into the law. So that's also something that is worth mentioning. And then there's this last thing in here that that's basically an inverse R squared law, inverse square law. Basically, this square somehow appears in here. So this might also be something that is worth mentioning. Okay. I mean, these are some significant issues in here. Whatever. So, I mean, this is something that's an additional law, right? It's the second law that we see. So the first laws that we have seen are the Newton's laws of motion. This is the second fundamental law of nature, all right? So let's first handle this point particle issue, okay? So that's something that Newton has shown, all right? The problem is like, so what is the force between two large objects? Okay, something like this, for example. Okay, so in that case, the thing that we should do is like we have to divide each of these objects into small particles like that, right? So each of these pieces apply a force to each other given by the previous expression. But in any case, so if you just consider all of these other particles that make up this body in here, all of them basically will be applying different forces on this piece and all the other pieces in here. So at the end, we have to compute the total force in here. So that's the total vector force. Okay. So as a result, I mean, computation of that total force somehow involves a complicated calculation. So let's see it like this. This F tot is the total gravitational force. Okay. This can be done by integration. So as a result, you have to know some calculus to be able to do this. So we are going to carry out some of these calculations in the second semester, but not in the semester. In the semester, we are assuming that you don't know anything about these kind of integrals. I'll talk about these kind of things later, but I'll just look at only one, the special case, because this is an important special case. Let me just go like this. If the bodies are, let's say, spheres with, all right, let me just add this spherically, all right, let me write rotationally symmetric. Mass distributions. If the bodies are spheres, then Newton's law is valid provided R represents the distance between centers. Okay, so that's the basically the problem that Newton have solved, right? Let's just do it like that, right? If I have like two spheres, two spherical objects with some certain mass distributions, but mass is distributed on them in such a way that the distribution is rotationally symmetric. So that essentially means that if I rotate the sphere, I still get the same distribution, okay? So sorry about this. I'm just going to use this perfect shape in here. I mean, at least a few times in the whole semester. I mean, let's use these things, all right? I'm also going to do that, right? Okay. So in any case, so they have some center in here and another center in here. This has mass M1, this has mass M2. And the distance between their centers, I'm going to use this color in here. So it is that distance. This is given by little r, okay? So in that case, it appears that the net force that's applied on this one, the total force that I have mentioned before, it still has the same form, right? That's basically G times M1, M2 divided by R squared. So basically, Newton was able to show this. Okay, I'm just going to say it like this. In the second semester, we are going to prove a similar kind of a thing for electric force, for the Coulomb force between two charges in a way, right? But by using some other mathematical way of solving, looking at these kind of problems, right? So the essential idea is this, basically to be able to compute this force in here, you have to compute all of the forces that act on the different parts of that object in here. Right? You have to be able to compute all of these forces and add them up. And mathematically, this is a complicated calculation. So Newton was able to do this. We are not able to do this right now. And so as a result, I'm just going to skip it and I just give the result in here. So that's something that you can accept in here. So somehow for spherical distributions, this is basically true. And because of the symmetry, of course, this force also has the same direction. And because of the Newton's third law, the force applied on the other object is going to be the same. It's going to be the same with the magnitude. With hyperbola, okay, so there's some kind of a talk in there, but I didn't understand what's going on in there. I may answer some of these questions in the break. Okay. So I think Newton actually proved like two theorems. One of them was this, that the fact that these are spheres doesn't change anything. So you can basically compute the force between two spheres, assuming that all of the mass of these spheres are concentrated at their centers. For the gravitational force applied by the Earth, for example, we actually use this, okay? We use this principle. There's another one, another mathematical theorem that Newton was able to prove. I'm going to mention this later, all right? That's basically for spherical shells. Okay, so the next thing is this. Let's mention everything in order. All right, so we have handled this part about, the point particles. So I don't need to deal with point particles usually. Okay, so the next thing in here is this. So if one of them is an extent, it doesn't matter what it is. Okay, so if I have one of them, let's say that is a very small object. Let's say this has M2 mass and this has mass M1. And we're talking about this distance in here, the distance between the centers. Okay, so in that case, the force applied on M2 is, right, this F in here. So let's say, all right. So let me write it in here. Force on object with mass M2 is basically that force is equal to the gravitational constant times mass of the big object, mass of the small object divided by r squared. Okay, so what's important in here is that this is proportional to M2. So as a result, we can then express this as M2 multiplied with the some number. And here we just call G as the, where G as the G times little mass, M1 divided by R squared is the value of gravity should we define gravity as a vector? So I'm not sure about this. So this, the magnitude is the value of gravity at the location of. We have to define it as a vector, right? Okay, so at that location, then we somehow define a gravity in here. I didn't write down Newton's law of gravitational force in the vector notation. I could have, because there's also a direction involved in there, but let me just skip that step in here. So let's say that this force then can also be written as M2 times G. So G has this magnitude, but it has a, basically G is directed towards the center of, let's say, big sphere, right? I mean, we're basically finding what we have actually been saying before. So there is this gravity vector, which is pointing whatever towards the center. Its value and its magnitude depends on the location. So at a different location, it's going to have a different direction and different magnitude. Okay. But especially this is important. So in any case, we can somehow compute the value of gravity as a function of our distance from the Earth, for example. Okay. Less than say a few things in here. So when people talk about the gravitational field produced by the Earth, for example, they actually talk about this value in here. Just a moment, let me think a little bit. So yeah, I'm going to explain what constant G means in a moment, all right? Yeah, there are a few things that I need to say in here. Yeah, let's just say it like this. So in any case, that's the important thing in here. So M2. So if so that's M1. If no other force acts on, yeah, let's say, yeah, sometimes we use this kind of a language in here. So if no other force acts on M2, but I should actually say that it's like, yeah, let me just use it correctly. So if no other force acts on the object with mass M2, M2 is basically the value of the mass, it's not the name of the object. So if no other force acts on the object with mass M2, then its acceleration is the local gravity, right? That's something that we also somehow knew from the previous chapters. But in any case, so basically we have this thing in here. So the force applied on M2 is basically equal to is mass times its acceleration. So let me also call this as A2 in here. So we know that the force is equal to M2 times G, and the masses cancel, so therefore A2 is equal to G, okay? So basically all objects have the same acceleration independent of their mass. All objects at that location have the same acceleration independent of their masses. That's basically something that we have stated like in chapter 3, basically, chapter 2, when we have talked about the free fall motion. All right, free fall motion. All right, there are a few things that I forgot to say. So let me, first of all, write this thing down. So gravitational force is weak. So basically, let's just say it like this. So suppose you have like, there are like these two friends with a separation of 1 meter away from each other. So let's say that their masses are like M1 and M2 are like about 100 kilograms. I mean, I'm just taking a typical distance between these two people. In that case, the force between them, like in that case, I can use this expression, but since these are not spherical objects and R is not really the distance between their centers, this only gives me an order of magnitude estimate of the actual force. So that's not the real force. It's just an estimate, right? Estimate of the force between these two. So since this Newton's constant is very small, even though the masses are large, distance between them is 1 meter squared. So what we get is like 6.67 times 10 to the minus 7 newtons. So that's going to be like 10 to the minus 6 newtons. What's 10 to the minus 6? It's like 1 micronewton. Okay. So basically, this is too tiny, right? It's like it kind of corresponds, the force applied by these two people to each other is actually smaller than the weight of an object with a mass of 0.1 microgram, right? So as a result, we never feel these in our daily lives. So as a result, we don't experience this force directly because it is weak, okay? So that's the first thing. So as a result, it is hard to measure this in the lab. So, I mean, because in the lab, we cannot have huge masses. We can have like perhaps a 1 ton mass or 10 tons of mass, perhaps, but it's not larger. In all of these cases, whatever the masses are, the forces are always tiny, right? So as a result, it's always a challenge to measure these kind of forces. Okay, so this is called the Cavendish experiment. But let me kind of explain it like this, or let me actually show the from my sharing screen. Yeah, I'm going to screen share. So Ötves experiment is something else. It's the Cavendish experiment, right? So I'm just going to show you the Wikipedia page, right? So you can actually do this experiment in the lab, whatever. So it's some kind of an historical experiment. Is there a better figure? Yeah, that's probably better. So what you do is like you're just hanging some object with a dumbbell. So you're hanging a dumbbell, and so you just arrange the masses in such a way that it just doesn't rotate, it just stays like that in any case. So, I mean, the situation is something like that. So these are, I think, the lead blocks or lead spheres or something like that. In any case, they have the same mass. So what happens is that you just bring in some other object in here, and then because of this weak force in here, this is going to just slightly rotate, and you try to measure the amount of the rotation in there because somehow you can relate this rotation to the force applied and whatever. So Cavendish was able to measure this force in the lab. So in any case, since the masses are known, it's basically, he's the first one to actually measure the gravitational constant. So it's basically the, actually, this is the only way G is measured, right? That's the purpose of that experiment. Before that, Newton was actually only guessed the value of the that gravitational constant, right? It was just a guess because he had some idea about the size of the Earth, and he has some idea about the density of the Earth. And from this, and he also knows the gravitational, the value of gravity at the surface of the Earth. And so he was then able to guess the value of G in here. However, Cavendish really did this, okay? And then, so he just basically computed this by doing an experiment. In any case, the problem is that you cannot attain a very high accuracy by doing this experiment because you are essentially trying to measure a very tiny effect in some, I don't know, in some system where there are all these other forces, for example, around, which are quite large, like air friction would actually be, if there's some kind of an airflow inside the room, air friction would also be somehow will be probably bigger than the effects that you're trying to measure. So as a result, the accuracy is always low. So that's low accuracy. And that's the reason why this G is actually known like with 3 significant digits only. They couldn't, I believe, I mean, they have done some modern experiments, so they just try to improve the accuracy, but they couldn't do it better than I think. I don't know. I mean, probably you have to look at NIST or somewhere else to actually read the modern value of this. Is there a way to calculate? No, it's not. It's something that it's a fundamental constant of nature, right? It has something to do about the definition of masses. So there's some kind of a hint in here. In any case, so when Cavendish has done this experiment, he actually announced it as he measured the mass of the Earth, right? So the idea in here is this. So, right, let's just think of it like this. This is the Earth, right? It has a mass. I don't know what the mass is. So we only know the density at the surface of the Earth. We don't know the density of the Earth inside, right? But in any case, so we know that the value of the gravity in here is given by G times the mass of the Earth divided by the radius of the Earth squared. Okay. The radius of the Earth can be actually computed by various means. It was actually first measured by Greeks, Aristophanes, probably. He was able to measure the radius of the Earth by just looking at the some wells, and then, yeah, there's a nice story about this thing. In any case, so Newton had some kind of an estimate. Columbus had some kind of an estimate as well. It was not perfect, but in any case, it was actually a well-known figure at that time. So it's like, we know that this is like 6,400 kilometers, around that value. It's not Thales, Eratosthenes. Yes, thank you very much. Eratosthenes, right? And the story is something like this. So there's light coming from the sun, and yeah, you know that the story in here. So there are places where this light somehow falls perpendicular to the Earth. You just need to find those places, and you need to then find some nearby place in here where it's basically falling with an angle. Just measure that angle and then measure that distance and whatever. That's basically the story, right? In any case, even Greeks were able to measure the size of the moon and the distance from the Earth to moon. You can read the stories from somewhere else, right? So in any case, so this was a known figure. So the only unknowns in here were the gravitational constant and the mass of the Earth. Newton had neither of them. And so as a result, he had to estimate the mass of the Earth and then get an estimate of G. Okay. But Cavendish was able to measure this gravitational constant. And so therefore, by using this known value, he was able to measure the mass of the Earth, right? And so as a result, he said that effectively he has measured the mass of the Earth. All right, so when we are measuring like the mass of the sun or mass of the moon or Jupiter or whatever, all the other planets and all the other stars, this is essentially what we are doing. Later, I may come back to this, okay? I mean, we will be basically using this kind of an equation to get their, to evaluate their masses, right? That's one way of actually measuring their masses. Another thing in here, so gravity, G, depends on location. Okay, so how does G differ by one differ when altitude Yeah, let me say it like this. How does G change? How much does G change when we go up 1 meter, 1 kilometer, or I'm going to say, yeah, let's say 1 kilometer, and how about 400 kilometers? Okay, I mean, I'm just going to start with this question, right? So we know, I mean, we basically treated that the gravitational constant is the same everywhere when we are solving this projectile problems. And the question is, how good is this approximation? Okay, and then I'm going to kind of say that, well, it's pretty good. Even 1 kilometer above the ground, the gravitational constant doesn't change, sorry, the value of the gravity doesn't change much. I'll talk about this later, right? But let me just start this thing here. So in any case, what I'm going to do is this. So I'll first look at the value of the gravity in here. Let's say that this is G. And then I'm going to think about gravity at a different location, let's say, with an altitude h above this point in here. And I'm going to compute G prime in here. And I'm just going to compute this value, and we will see how it differs from G. All right, so I'm basically going to compute this difference in here. Okay, so how can we do this? I mean, there are different ways of doing that. In any case, let me exaggerate and then show that this is the radius of the Earth, right? So in any case, so what we need to do is like this: G is equal to this G, the mass of the Earth, divided by the radius of the Earth squared. The value of the gravity at a height h above is G times the mass of the Earth divided by the radius of the Earth plus h squared. Okay. So the radius of the Earth is like 6,400 kilometers. And the height that we are thinking about is like 1 meter. So therefore, this height is much smaller than the radius of the Earth, right? So so basic idea in here is that this is actually very close to the radius of the Earth. And as a result, this G prime is very close to G, right? So as a result, normally, we wouldn't actually care about that change in here. And we would just insert the radius of the Earth in here in computing this. But in any case, right, we know that this is quite similar to this one, but we know that they differ, and we would like to know how much they differ, right? So this is actually some kind of an interesting calculation that we do from time to time. So as a result, I'm going to spend some time on doing this, right? This has nothing to do with gravity. This is one type of calculation that the physicists do. And so as a result, I'm going to spend some time on this. All right. So how can we do this? So how can we compute delta G, right? So G minus G prime. Why do I subtract them like that? Because I know that this G prime is actually smaller than G. All right. So as a result, I get a positive value. Right. That's the reason why I do it. I do it like that. So that's basically the difference between these two quantities. Okay. So first way. So that's the long way. But this is the kind of the best way to compute it. If you don't know anything, if you don't have these tools, so you just compute it in that way. So you just compute it like this, like the way that everyone would do. But in any case, what you need to do in that case is basically you just manipulate this expression, right? So that's basically GME times RE plus H squared minus RE squared divided by RE squared times RE plus H squared, right? Let me write it down like that, okay? So let me also take this inside the square braces. Okay, then we expand this part in here. Okay, so this is G times ME. Let's see, if I do this expansion, I get like the binomial expansion plus H squared, and the first term just goes away. All right, so I'm doing this right now precisely. I'm not ignoring anything in here. In any case, you can see that in the numerator part, we have obtained an H. So the numerator is proportional to H. So we know that H is basically small. H is much smaller than RE, to be precise. And then we find an expression which is basically proportional to, in a way, the small quantity, right? So this is a point where you stop in a way, and then you try to simplify this, right? So again, this part is still exact. I didn't ignore anything. So these are all exact. But right now, I don't need that exact expression, right? So, because the idea in here is that I just obtain this little h in here. So I know that this expression will be non-zero. So at this point, then I can then eliminate all h's when they are next to this RE. So let's say it like this: at this point, right? Replace all h that appears next to RE by zeros. All right, so that's the important part in here. So the essential idea is that it's not h small. H is 1 meter. It's not small for us. It is so small compared to something, some distance, and in that case, it is the radius of the Earth. It is small compared to the radius of the Earth, and as a result, it is at this point, for example, right? It is at this point where adding an extremely small thing to RE doesn't change this value much. So as a result, at this point, you can replace this h to be equal to 0. In here too, it's 2RE plus h. I can also replace this one to be equal to 0. We're just ignoring them actually, because they are not going to change the calculation in any significant way. Okay, but I don't ignore this, because if I replace this thing with 0, then everything else will be 0. So the effect that I would like to compute would be gone in that case, all right? So that's something that I don't ignore, so that stays. So let's say it like this. This stays in here, because that's basically is the thing that I would like to compute, okay? So in any case, basically in the rest of the expression, the h goes away. So let me write down one more step in here. So that's 2gme. We have 2re times h in the numerator and re to the power 4 in the denominator, okay? So as a result, this is like 2 times g times me divided by re cube times h. And then you compute this. However, in these kind of situations, there are also some easier ways of handling these. So I don't want to compute, like multiply the gravitational constant with the mass of the Earth and then divide this. Yeah, I mean, there are too many values that I deal with, but I know that this particular product, g times mass of the Earth divided by the radius of the Earth squared, is equal to gravity, okay? So as a result, I can write down the first expression as the gravity divided by the radius of the Earth times h. So that's delta G, okay? And in this form, this is actually also dimensionally correct. So we have the difference in the values of the gravity is equal to the surface gravity multiplied with a dimensionless number in here. basically is the multiplied with the ratio of two distances. Okay, so let's then compute this. So this is, I know that this is like 9.8 meters per second squared. It's 10. So if this is like 1 meters, and the radius of the Earth is like 6.4 times 10 to the 6 meters. So that's 2 times 1, right? So I'll just take this as 10. So that's 10, and this is like 1 over 3.2 times 10 to the 6. So that's like about 3 times 10 to the minus 6 meters per second squared. Okay, so that means if I somehow know the value of the gravity, let's say it like this, 3, 1, 2, 5, I'm just writing random digits in here, 2, 8, 9, and whatever. I mean, if I measure this like with very high accuracy, like with 10 digits of accuracy, all right, if I go 1 meters above, that is the digit that would change, right? That digit changes. And all the rest basically also changes when we go 1 meter above, when we go up 1 meters, right? So this part doesn't change. So as a result, if you don't know what these things are, so that means that this changes, this dependence on distance is negligible, right? So even though we know that the gravity depends on the location around us, that dependence on location is unimportant. So as a result, around us, we can assume that it is constant. We can more or less assume that it is constant, okay? So I can basically go ahead and then talk about what happens if I go 1 kilometer above. In that case, this thing changes, right? This is like 1 kilometer above, sorry, 1 kilometer above. That digit is going to change. And if I go 100 kilometers above, in that case, this second digit, I mean, the first digit after the decimal point is going to change. And interestingly, this is the location of the satellites. Okay, so that's one of the interesting things. So ISS, I believe, has an altitude. I'm just going to look at this figure in a moment. ISS has an altitude like between, I believe it's like 300 kilometers or 400 kilometers. So from this calculation, you can kind of guess that, well, at the location of the ISS, the value of the gravity is more or less the same. It basically changes like about 10% or something like that. Okay, in any case, so let me stop here. In the beginning of the second hour, I'm going to do the same calculation, but this time I'm going to do it in an easier way. The way that you should be doing, because it's kind of much faster and you don't have to know anything new. You just need to remember the Pascal's rule, binomial expansion. Okay, so let me stop here.